Screencast-O-Matic going, and PowerPoint. And you've heard all the announcements. I should have marked the roll before I turned that on, because that won't be too hard to do. Josh is here, and Bill is here. Second verse, same as the first. Okay. All right. Any questions on anything we've done so far?
Yeah, I wanted to go over making the exact equation D of M to N, D of F to M. When we get to going back to the F function, it makes a substitution.
Oh, right.
I have a problem with that.
Okay.
I mean, I'm looking at it here where they give you the method of doing the steps. Somehow I get lost in it.
Okay. Is there a particular problem you're lost on it, or an example? Huh?
The theorem itself.
Okay. Put this back in place here. Okay. Let's see. I don't know if this will help or not. Okay. Trying to figure out whether to start with the chicken or the egg, I just don't know which. If you have, and this is, I think, where they started, let's see. Let's just start someplace. Let's say that there is a function f of xy equal to a constant. Okay. Now, if you take the derivative of that function, and part of this is based on the fact that deals with partial derivatives and stuff like this, but what you would have is partial of f with respect to x. Let's say we're taking the differential of this, dx plus the partial, I can't write, of f with respect to y dy. That's going to be 0. Okay? If you take the total derivative of the left-hand side, it's the partial of f with respect to x dx, and then you do the partial of f with respect to y dy. That's taking the derivative of everything you got here. The derivative of the right-hand side is 0. Okay? That's where we started this whole. At some point, we started the process. Now, what you're usually given is not this, though. What you're usually given is this. Some m of xy dx plus some n of xy dy is equal to 0. Right? Okay. Now, the only way that this will work, well, the first way that this will work is, and that we do where we do our test, that if the partial of m with respect to y, the other variable, is equal to the partial of n with respect to x, then we can proceed. Then that implies this is an exact, I can't write, exact differential. that implies it is an exact differential, and that's what we did, okay? So as long as that condition's met, we can proceed, okay? So I'm going to assume that condition is met. We've already verified it, so let's get rid of this for now because we don't need this in the solution. That was just to make sure we have a solution. If those are true, we will have a solution. Now our effort is to find it, okay? So here's what we do. We basically start off, and either one of them would work. It doesn't really matter. We want this m of xy to be the partial of f with respect to x has to be our m of xy. Okay? We don't know the function. Let's see. Up there we knew the function, and we did this. And then we said, this is how it will look. Okay, now pretend we don't have that. We just know this, and we verified through our test that it is going to work. So now we're trying to find the f, so we're going that direction now. So we know whatever f there is, if there is an f, the partial of that f has to be the sum of xy. Okay, whatever function that is. Okay, and then what we do is sort of cheat a little bit and write that sort of in differential form, integrate both of those. Now this gives us f of xy. And when you integrate this with respect to x, you still are going to come up with a y, but this gives you whatever that is. Okay. This is a function that is integrable, so we're going to integrate it only with respect to x, leaving the y's just like they were constants, just integrating with respect to x. And this just gives us a function of x and y again, so I'm just going to leave it like this, integral of m of xy dx. Except you could have a constant, but a constant with regard to y, which could be a function of y. Because the integration with respect to x isn't going to mess with any y's. So you could have a constant or some function of y only. Okay. Now, that used this equation and this fact, okay, to get us this formula. Okay. Now, let's take the partial of f with respect to y, and that's got to be that thing, right? Okay? But we're not going to do it here, we're going to do it here. We're going to take the partial of this thing with respect to y, okay? Make sure I'm not jumping ahead of myself here. So the partial of f with respect to y, this thing here, is equal, and we got to do it here, partial with respect to y of the integral of m of xy dx. Okay. But when you take the partial of the second part, that's not a partial anymore, that's just dg dx. dg dy. Goodness, I can't talk. Okay, dg dy, or y, or g prime as the book calls it. Okay. Now, this thing has to equal your n of x. Okay, because that is what this is. So when you take this derivative, now, remember this thing here is some function of x and y, and you can take the derivative partial of this with respect to y. That's going to give you some value. And this g, we don't know what it is, but that's dy dx. But we know what this one is. So now if we subtract this from here, that gives us what dg dy is. So subtract partial with respect to y of integral of m of x, y, dx from both sides. Okay. Now, so you've wiped these out, and now you got dg dy is equal to n of xy minus partial with respect to y of integral of m of xy dy. Okay. Now remember, that looks complicated and stuff. That's just an integral you could perform, and you did. And then you took a partial, and you did. Now, those two, when you subtract them, you better lose all your x's. If you started off, if everything was true that you had before, you're going to lose all the dependence on x. And then you're going to wind up with just dg dy is equal to some function of y. That whole thing will be some function of y, and you integrate that function of y. You just write it in differential form. Wait. I got ahead of myself here. This is a dy, dx here. And then all this multiplied by dy. But this has to be just some function of x. Your y, no, I'm sorry, some function of y, because your x's have subtracted away. They've got to. Otherwise, you're going down a rabbit hole that isn't going to work. Okay? And what you do now is integrate both sides. Okay? Of what's left. And that's usually a pretty soft, reasonably good to do, and that gives you some function of y. Okay? Now, whatever that happens to be, whatever that is. Okay? And then you take this, plug it back in here, and there's your alpha of xy. This is some function of y alone. This was a function of x and y. Plug it back in, and you have a function of x and y. Now, at that point, that's your alpha of y. That's not your solution. Once you get this thing, then you go back and set it equal to c. That c that you had before, because that's where you started from. This function that you went all the effort to get, you did this part to get this, you did that part to get this, and then when you combine those together, you wind up, that's your alpha of xy, you set that equals c, that's your solution. Not the alpha of xy, this thing equals c. That's the part that sort of always threw me. I'd stop here and think, well, I find my solution. No, I haven't. I set that solution, that function equals c, that's my solution. We don't know what the c is unless we're given a boundary value problem. But see, that before, it was after we did an integration, we got our c's. Now, we get our c here. This whole process, once you have the alpha of xy, that's equal to some constant. Now, if they give us a boundary value, which we're going to do today, then that will help us determine what that value of c is. That will be our solution. I don't know if that's any good or not. Was it?
Yeah, that helps.
Okay.
It entirely helps. Just got to play with it.
Yeah. It's so confusing looking at this because you got your function here, you integrate it, then you take a partial of that integration, and then you undo that, and you subtract. Well, the thing is, this is just some function of x and y. Then when you take the partial of that, you simplify the y's, but you leave the x's alone. When you integrate this, you leave the y's alone, but integrate the x's. Then you differentiate here, and you fiddle with the y's, but not the x's. And then when you subtract these two from each other, that leaves you with some function of y alone. this is the one that we can integrate that one to get the G, plug that back in here. And again, this is some function of x and y, this is a function of y alone. That gives you your F. Forget about the F now, set that equals C. And that's your solution. That last part, setting it equal to Z, C, I always would forget because I thought, oh, here's my F of x, y, there's my solution. No, it isn't. It's that thing equal to C. That's your solution. Because otherwise, you never, when you did this integral, you didn't put a plus C. When you did this integral, or whatever, yeah, you didn't do a plus C. I mean, this integral, you didn't do a plus C. You never did a plus C. You're waiting till the very end, setting that equal to C, and then that's your solution. So I don't know if on the other hand, it's magic. I don't know. whichever suits you better. Okay. It does give you the answer. All right. And example 3. Any other questions? Good question. I don't know if I answered it well or not, but that was a good question.
I did what you did. I said, I got the solution.
Yeah. Okay. All right. So let's do example 3, which has an initial value problem, which has an initial value, which is going to enable us to figure out what that C is. Not at the beginning, at the very end. So you go through it all. So here, ooh, goodness, look at this. Okay, so solve this. dy dx is equal to xy squared minus cosine x sine x over y times 1 minus x squared. Okay? Given that y of 0 is equal to 2. There's your initial condition. Now, most of the time in calculus, when I see something like this, I want to write down something right off the top, just to remind myself so I don't start heading down a path that's not going to get me anywhere. And the thing I want to write down is y can't be equal to 0, and x can't be equal to what? Or? Yeah, okay. So let me write that down. Y cannot equal 0, x cannot equal plus or minus 1. And notice our initial condition is y of 0. So x can be 0, there's nothing wrong with that. And y is equal to 2, that's okay. Y just can't be 0, it can be 2. Okay. So with that in mind, before I ever start, because once I start going, I'm going to forget about that. Okay, so I like to write it down near the beginning. All right, what would you do next? Do you think this may be separable? Any ideas? I don't think so either. In fact, in no possible way whatsoever can that be separated. That denominator could be separated. The numerator cannot ever be separated. Okay? So, nope, hang up separation of variables. Do you think this might be linear? Right. Yeah, because, there are a couple of reasons. If you broke that numerator into two terms, that first term would be okay, because it would be y, one of the y's would cancel out, and you have a x over 1 minus x squared. That's fine. There's just some function of x times y. That's okay. And then, but the second term would then have a y in it, okay? Because you have, and that's not good for your constant, because that can only be a function of x. If you multiplied everything by y, then you multiply this by y, and that's not good. So no, it's not linear in y, And it's sure not linear in X. Okay, because cosine and sine, neither one are, and X squared, no way it's linear in X. So no, can't do either one of those. So basically our only hope right now is if we can do it exact. Now later we'll have some other tools, but so far those are our only three things. Can you make that look like an equation that at least we could consider whether it's exact or not? What would you do?
I'd multiply both sides by
that denominator, okay? So that will give me a y times 1 minus x squared dy. I'm cheating a little. Yeah, then xy squared minus cosine x sine x dx, okay? Now, I haven't figured out whether I want to multiply through by y or not. I kind of don't want to, but I might need to. But anyway, our standard form would then be to write this something like this. Xy squared minus cosine x sine x dx plus, I'm going to flip things around. I think I will multiply through. X squared y minus y dy. Okay. What I did, I subtracted that. I kept this positive. I don't know if that's good or not. And then I moved this to the other side, so that reversed the order.
Oh, I didn't even notice reverse
the order. Yeah. Okay. And did that. Just to get it to look like that. Okay. And you could have done it the other way. You could have flipped these and moved it over here. I don't think it matters. We'll see. Okay. The answer should come out the same, but whether it gets more difficult. Now, what's the next thing we got to do?
You have to find M.
Okay, I think I can find this. That's an M, and that's my N. But what do I do with it once I found it? With respect to what?
First one is X. M is X.
Yeah, okay, it's M of xy, right? But you take the partial with respect to y, exactly. That's our test. That's not part of solving the problem, it's just our test to see if we can solve the problem. So let's do that. The partial of M with respect to y. Okay? And what would that be? Two xy. Done. Because the rest are x's. Right? Okay? Now let's do this one. What do we do here? To x. And what does that give us? 2xy. Done. Yes. Those are equal to each other. You know this is an exact differential. So since it's an exact differential, we don't need this anymore. We verified it is an exact differential. So let's get it out of the way because I don't have room. You don't have to erase it. Keep it on yours, but I don't have room enough. So I'm erasing just for that reason. And now, do you have a preference on which we do first? We could go either way. Either start with the, okay, let's write down what our assumption is. Since it is an exact differentiable, you know there's some function of x and y equals c, that thing there, that this satisfies. That's our assumption. Okay? And with that assumption, you know that the partial of f with respect to x is equal to this m, and that the partial of f with respect to y is that n. Those are the three things we know. That's our answer when we finally can find it, and these are the two pieces we're going to use to get there. Now, we start with one of those two pieces there. You tell me which one you want to use. Huh? M? Okay. He's sold on M. So what we're going to say is the partial of f with respect to x is equal to this xy squared minus cosine x sine x. No, what's going on with the dx? That doesn't go there. That's the m part. Okay. Which, now we're going to wipe out that squiggly x and put a dx here and integrate both sides. Right? Okay. An integral of a derivative is f. F of xy is equal to, now, antiderivative of that one. Since you do it with respect to x, leave the y just like it's a constant. Okay? It's what? Y squared. You're not taking derivative, you're integrating. X squared over 2. Okay, now let's do the same for that with respect to x. Well, there are no y's in this one, so let's do that one. And which would that be? Okay, you need to go off to the side. Huh?
Would it be just a C? Is it just a constant?
No. There, you got to integrate with respect to x. What you're integrating, I'm going to leave the minus sign outside of it. Integral of cosine x sine x dx. That's what we're integrating now.
Minus a minus sign, and then, let's see, sine squared.
Okay. Over 2 probably too, one of it.
And then we have to do plus.
I think that'll do it right there. Okay? I think that's the antiderivative of that. Let's see if it is. I'm forgetting about the minus sign. Okay. Derivative of this would be 2 sine x times 1/2, 2 and 1/2 cancel out. Times the derivative of sine. That's exactly what we got there. Right? Yay or nay? You could do a U substitution if that makes it any clearer. I think it'll come out exactly that. Okay, so that's going to be a minus that. Okay, so it's going to be minus sine squared x over 2. And one more thing. Plus g of y. Because that would have been our constant had it been a constant, but because we're integrating only with respect to x, it could have a function of y there that if you took a derivative of that, that's just going to be 0, so you get right back where you were. Okay, so I think we're all right there. Now, what are we going to do next? We're going to use this second one. See, we used this to begin with, and that's how we did that. Now we're going to use this one and see if we can figure out what that g is. Okay, so we're going to say the partial. What's that? What's that? Okay, if it's cosine squared, that would be a plus then, wouldn't it? Because the derivative of cosine is minus sine.
Oh, you're right. I just did it with the minus.
Okay. Okay. it'll be the same thing as here, except there'll be a plus here if you use cosine squared, I think. Okay, check me on that. If we integrated that and let the u be cosine x,
Yeah, that's what I do.
okay, and then du would be minus sine x, that would wipe out this, make it a plus, right? Okay, and then you get cosine squared. So with the plus here, cosine squared works the same way. Yeah. But it would be a plus. Right? I hope so. I hope I'm not leading you down the primrose path, okay, where there's lots of thorns. Okay. So let's do the partial of this f with respect to y. And that had better be, and I wish I had left more room here, we're going to do the partial of this thing with respect to y. And that had better be this. You're in, which is x squared y minus y. Okay? We'll get there later, but that's what it had better turn out being. Okay? So let's take the partial of this thing in parentheses with respect to y. Yeah? No, derivative. Taking a derivative, not an integral. You're doing the partial of this with respect to y. Later we'll integrate, but not now. Yeah, okay. 2 times 1/2 will be 1, x squared y. Right? Minus, take the partial of that with respect to y, and what do you get? Hint, that's x sine squared of x over 2. Zero! There is none. Plus, and derivative of this with respect to y is dg, keep one second, dg dy. Okay? And that's equal to x squared y minus y. Okay, guess what? There goes the x's. We had to get rid of those, right? And we did. Okay? Now, that leaves us with dg dy is equal to minus y. So let's write that in differential form. Integrate, and g of y is equal to what? Minus y squared over 2. Right? That's your g of y. Let's plug. Okay, got it? Or,
Yeah, I was just saying the same thing.
okay, let's plug it back in here. Now this is before we did the d by dy. Okay? Okay. So here we go. F of x, y is equal to x squared, y squared over 2 minus sine squared x over 2 minus, because it's plushy, y squared over 2. Okay? But that's really not what we want. We want to set that equal to c, because that was our assumption here. That's our alpha of xy. So forget about the alpha of xy now. That was just a construct to get us where we needed to go. So there's our solution. Now, since that's our solution, we can multiply everything by 2 and get x squared, y squared. This is so aggravating. Minus sine squared x minus y squared is equal to, you want to name it a different c, or can I name that c? Okay. Yeah, you knew it. Okay. I'll make that C1. Now it'll be a C. Okay. Now what we have to do is apply our initial condition. that y is equal to 2 when x is equal to 0. When x is equal to 0, that first term's going to be 0, right? This is our x, this is our y, right? So when x is 0, that first term is 0. And the next term is 0, because sine of 0 is 0. So now we have that minus 2 squared is equal to c. So what is c? Negative 4. Okay, you square the 2 before you negate it. Okay? Now, our solution is x squared, y squared, minus sine squared x, I can't write, minus y squared is equal to negative 4. Goodness gracious, quit doing that. Okay. Or you could add do a plus 4 and have it equal 0. But that's our solution. Okay. Let me see if I can find it here. Okay. Now they do one more thing to it, so let me do it too. So I'm going to take that solution I just did. I'm going to put the first and last terms together and factor out the y squared. So y squared times x squared minus 1 minus sine squared x is equal to minus 4. Or, because you got so many minuses in there, you can multiply everything by minus 1 and make that y squared times 1 minus x squared. And that looks a lot more like this was to begin with. Okay, plus sine squared x. Let me erase some stuff so I can write it all down here and make it make sense. Because we just did this up here as extra work. Okay, plus sine squared x is equal to 4. Okay, that I bet you is how they present it. What? Say again? Oh, well, there's a reason for that, isn't there? Okay, because we did sine squared. The book did like you did and put cosine squared. Right? Well, when you plugged in the x, cosine of 0 is 1, not, okay? So instead of sine squared, let's do it this way. Y squared times 1 minus x squared plus, what is sine squared in terms of x of cosine squared? 1 minus cosine squared x is equal to 4, right? Yeah, quit doing that. Okay, so this will be y squared times 1 minus x squared, and I'm going to subtract 1 from both. I can lose those parentheses. I just put them there so you know that was what sine squared was, is 1 minus cosine squared, right? So I can lose the parentheses, right? Without any damage to anything. And subtract 1 from both sides, right? Okay. Okay. Okay, so these go away. Minus cosine squared x is equal to 3. Does that make you feel warm and fuzzy? It's what was in the book. That's what the book got, right?
Yeah.
All we did.
We didn't do it wrong.
No. What we did was change the sine squared x to 1 minus cosine squared. Okay? So then we had y squared times 1 minus x squared. And the plus 1 is to subtract from both sides. cosine squared x equal 4 minus 1. That's the same answer. It's just we did it in terms of the sine squared to the plus, they did it with cosine squared to the minus. Those are the same answers. And you can plot them too. Okay. Now, where is that good? That's only good because your x is a 0. That means you're only between minus 1 and plus 1. You can't be less than minus 1 because you would cross the discontinuity. You can't be to the right of plus 1 because you would cross the discontinuity. So this is only good between minus 1 and that 1. Let me see. Okay. I should have put as an element of or something like that. All right. Now, to show you how that pertains, here is the family of curves that represents, and what an ugly family that is. But for that one particular value, when x equals 0, y is equal to 2, there's the curve. And you see it stays between minus 1 and plus 1 forever. It can't be out here, it can't be over there. So that blue curve is the one and only solution. All those others are potential solutions for any c that you put in there. But please let's not put an equal one. Okay. And that keeps you between minus 1 and 1. Make sense? Yeah, you'll say.
And I get why the C's are different. Just took me.
What's that?
I get why the C's are different things. It just took me a minute.
Right, yeah. And we don't like all those different things, do we? Okay.
No, but it's pretty cool.
Yeah, it is. It really is. Now, and they call it an interesting family of curves. If that's what you want to call it, you can call it that, okay? The graphs of the members of the one-parameter family of solutions, blah, blah, can be obtained several ways, two of which is using software to graph level curves, as discussed in section 2.2, using a graphing utility to carefully graph the explicit functions obtained for various values of c, blah, blah, blah. Okay. I don't think I want to do either one. Okay. Now, the last section, 2.3, we found that the left-hand side of a linear equation can be transformed into a perfect derivative when you multiply the equation by an integrating factor. That was our procedure for linear equations, right? Remember? We had to find that integrating factor. The same basic idea sometimes works for non-exact differential equations. M of xy dx plus n of xy dy equals 0, but then when you do the partial of m with respect to y and the partial of n with respect to x, and you find out they're not the same, and you say, oh no, we just hang it up. Or we can say, well, maybe we can find an integrating factor, mu of xy, that when you multiply both sides by that, you now have produced an exact differential. Likely, huh? In an attempt to find mu, we turn to the criteria 4 for exactness. Now that's back on page 65, and that's the thing at the bottom. The partial of m with respect to y, the one, our test, okay? We turn to that, okay? All right, I'm going to clear this up. They say the proof is in the pudding. Some of these puddings are really messy. Okay. And this is another one of them. You can get so lost in the mechanics of it, you almost
get what you're solving.
Yeah, you lose the forest for the trees, basically. You get just so bogged down with it. Okay? Now, what we found out is that M of x, y, n of x, y, when you have those two, this is the dx and this is the dy, and you do the mesh to it, you don't get an exact differential. It's not an exact differential. So now we're going to multiply mu of xy by both of those. I wish I'd left more room. Okay. Now, we don't know what the mu is yet. Okay. But what we want is that I'm going to use the shorthand notation. I don't know if you're familiar with it. The mu of xy, m of xy, this thing, we're going to take the partial with respect to y. Okay? And that means taking the partial with respect to y. That's we haven't talked about that before, but it's just a shorter way of doing it. Is equal to mu sub xy, n sub xy, and taking the partial of that with respect to x. Okay?
So is mu going to be the same on both sides?
Yes, it is. In fact, they drop the xy's everywhere. Okay? Now let's do what they just said here using the product rule for partials is the same as any other. So this will be, now which way do you like to start product rule? You tell me. We'll just forget about the of xy's now. Everything's of xy. Mu m sub y plus, okay, I'm going to put mu sub y m, it doesn't matter, same thing, is equal to mu n sub x plus mu sub x n. Okay, by that? All right. Now, what we're going to do now seems a little bizarre, but actually it makes sense. What we're trying to do is find out what mu is, right? So let's get all our mu's together and everything that's not a mu otherwise. Well, here we'll subtract a mu n sub x from this side, and we'll subtract a mu sub y m from that side. So do a mu minus mu n sub x and a minus mu sub y m. Okay, these go out, those go out. What we have left here is mu times m sub y minus n sub x is equal to, let's just leave this like it is, mu sub x n minus mu sub y m. Okay, so what is our mu? It's mu sub x n minus mu sub y m divided by m sub y minus n sub x. Okay? Now, what's that?
What about the mu sub x and the mu sub y?
Where? Up here?
Oh,
Right here? Okay, they're there. I mean, what we did, we factored out the u, and we divided both sides by this. So this is our numerator, and this is our denominator. Okay?
It's just hard to see without numbers, I guess.
Yeah, right. Exactly.
Variables, whatever.
Right. Yeah, not even real variables.
Yeah.
All right. Now that would be okay, except we don't know what mu sub x and mu sub y is.
Yeah, that's.
Okay.
I guess that's what I meant.
Yeah. We know what n is and m, and we can calculate these two. Yeah, those are fine. But we don't know what these two are. So it doesn't seem like we've made a lot of progress, does it? And perhaps I divided the wrong thing. Oh, no, I'm sorry. This is the part that drives me nuts, okay? It says, here's a statement here. Although, and I actually jumped the gun. So let me erase this last line, okay? And that was bothering you anyway, wasn't it? Okay. Okay. Now, in this last line that we've got here, okay, we know we were given this and that, and we can easily calculate this and that. In fact, we've already done it when we first tested. Okay? And we found out they weren't equal to each other, so the difference is not zero. Now, if the difference is zero, you don't need a mu. Okay? So, but we don't know the other two. Now, here's the thing. Although those four were known, the m's, n's, and the partials of m and n, are known functions of x and y, the difficulty here in determining the unknown mu of xy from this equation is that we must solve a partial differential equation, which we have not prepared to do. This is ordinary differential equations, so the only thing we're messing with now. Okay? Since we're not prepared to do that, we make a simplifying assumption. Suppose mu is a function of only one variable. Okay? So, okay. So why didn't we say that in the first place?
Why are we prepared to do that?
Huh?
Why are we prepared to do that?
To do the other thing? Solve a partial differential equation?
Why don't we just solve the partials?
Because that's a whole different course. Remember at the very beginning we said two types of differential equations, ordinary and partial. We're only doing ordinary. Partial differential equations, and in fact when I was in an undergraduate,
Oh, we were just taking partial derivatives.
we're just taking partial derivatives. We're not solving a partial differential equation. Okay. When I was an undergraduate, there was a 3-course sequence in partial differential equations. A senior sequence. You can only be a senior or grad student to take it. And you needed it. I mean, it was a bear. Bear. Okay. Now I had an instructor, a professor who made it worse of a bear. Because he said, I'm just going to assume you've already had Fourier analysis, even though it wasn't a prerequisite, and teach it as if you've had that. If you haven't, get out of the class. And I was on my way. A buddy of mine, other physics major, said, hey, he's just blowing smoke, Fowler. We can handle this. We've been through this. Yeah, he's just trying to get the class size smaller.
Never listen to your parents.
Okay, I learned. I scraped and managed to get the very lowest C in the class, but I made a C. And I think it was the first C I'd made in the math class. You know, but I was happy to get it. He failed. Okay. The guy who talked me into staying failed, and he was out. Okay. So everybody below me dropped dropped the sequence. So when we came back the next term, I was the bottom of the heap. So I was the lowest score to, I think I was anyway. So that term I scraped and scraped and scraped and just moved up because, but still made a C. And everybody below me dropped. So the next term we came in for the third in the sequence, and this time I scraped and scraped and scraped, and I thought I had a B within reach. And I was just within a point or two. And this was a totally elective course.
At least you were consistent.
Yes, totally elective course. And you would have thought the professor would have said, these guys have stuck with it for 3 terms, put up with all this. So give them a little slack. Make a 78 or 79 a B. No, it's a C. So that was my history with partial differential equations. I learned a lot, but boy, did I have to work my head off or some other body part. Okay. So here's a problem. We have something that can only be solved with a partial differential equation unless we make a simplifying assumption. Let's just suppose that mu is not a function of both variables, but only one. Okay? So, what if mu is a function of x alone? Mu function of x alone, not of xy, like we did up here. If that's the case, then let's solve this for mu sub x. If it's a function of x alone, then mu sub y is equal to 0. Okay, right? Because there is no y dependence. They're all x's there. There are no y's. You take a derivative of it. Yeah, so that's 0. So if that's the case, then we have this situation. Mu sub x, which is d mu dx. Now we're using the wrong notation. Okay, I said mu and wrote a y. And I almost wrote a partial when I meant to write a exact derivative. Is equal to, okay, this is now 0, right? Because it has mu sub y, is equal to mu times m sub y minus n sub x divided by n. Okay? And now, this has x's and y in them, but we've just said that mu is only a function of x. Okay? So it seems like we've dug our hole even deeper. Okay? Now, however, if after all the obvious algebraic simplifications are made, that quotient does turn out to be a function of x. And, it could happen, okay? Remember, this was something not 0, because the m sub y is not equal to n sub x. So this is not 0, but it could be that when you did those, it only came out, say, a factor times something, and if this n has that same factor of y in it, and those factors cancel out, then this could become a function of x alone. So if that's the case, first, if that's the case, and that's the case, then you can differentiate this, and this would all be a function of x alone, and multiply by dx, and do whatever it takes.
We're trying to find mu here, right?
We're trying to find mu, okay? And there's a mu here, and there's a d mu here, and that sort of stinks. So here's what we would have. If that's the case, if this turns out that you've lost y dependent, that this is a function, I write of and write it backward, of x alone. If that's the case, okay, if it worked out so that's the case, then you can write this equation down. Okay? Well, this would be your equation. D mu dx is equal to, I like to do it a minus m sub y minus n sub x over n. And remember, this is a function of x alone, right? Times mu. And mu is a function of x alone. And that's equal to 0. Well, guess what, folks? It's a linear equation in mu. Okay. If this is a function of x alone, then integrate that. Yeah. And then E it. Okay, you use such strange stuff. Okay. and go to town just like her good old.
Well, I really don't know what I'm talking about, but I can write it out.
Yeah, exactly. So, yeah. You first integrate it. I know it looks complicated here, but it's just some function of x. You integrate it. Remember, this is your p of x. Okay? You integrate p of x. Don't add a plus e or anything to it. And then whatever that turns out being, it, okay, do e to that, and then multiply that by, well, that becomes your integrated factor, okay? And you go for it, okay? Multiply both sides of it, and you'll get it to work out, okay?
That will equal mu.
That will be your mu. Yeah, okay.
So
you got to do all that. That's your integrated factor, which we used to call mu. But now we got a new mu. So call it something else.
Okay.
Rho, okay. Rho, okay. Whatever you want to call it. That would be the new integrating factor. Then you multiply both sides of the equation by that, and you have rho d mu is equal to, and this whole mess here would be, that is your rho mu, and then better be a derivative. Am I forgetting how to do that? I hope not. Don't mess with the linear. I'm sorry. It turns out to be separable as well. So don't worry with that. Separate the variables. So you don't have to worry with doing the other. Because this is a function of x alone. This is a function of x alone. So you have d mu over mu minus, or is equal to, move that back to the other side. In fact, don't even move it to this side. This thing here, m sub y minus n sub x over n times dx. Integrate this and you get log, integrate that and you get whatever it is. That's just some function of x, as long as it's integrable, you can do it. Okay. Well, what if? Oh, no. What if? What's that?
When it doesn't work.
When it doesn't work and mu turns out not being a function of x alone, and this turns out not being a function of x alone, guess what? We can say, well, what if mu is a function of y alone? And if mu is a function of y alone, then this is 0, this is that, and we have a new one. And then the condition would be not this, but it would be the derivative of mu, which is a function of y alone now, dy, if you take a derivative of it, okay? No, I mean, that comes out being equal to, if you turned all that around, it will be n sub x minus m sub y over m, I think this time, yeah, m times y. Not mu, I'm sorry. I keep writing mu's for y's and y's for mu's. I don't know where my brain is today. Okay. All right. And that's separable. D mu over mu is equal to this thing, which is now a function of y. So n sub x minus m sub y over m. That, if that turns out being a function of y, then that's times dy, and integrate both sides. That'll be a log mu. I know that one. The other one will be whatever it turns out to be. And then you can e this side and get just y, or I'm sorry, get just mu, and the e of whatever that is. That would be your integrating factor. Then you take that and multiply by this. Yeah, whichever one works, you multiply by that, and then you have a
This is just proving that they're equal if you have whatever your integrating factor is.
right, yeah.
Okay.
Yeah, what you would have to do then, oh goodness, is now your mu is only a function of one or the other, whichever one it turned out being. That mu times this, yeah, this one, you've guaranteed this is going to work now. Whichever one worked here will work up here. And now you go through the same thing you did with this mu function that you did before, and make it work. Okay. Now, that's the blah, blah, blah way. How much time do we have? 10 minutes? Is that enough time to do the example 4?
They only did it in 4 steps.
What's that?
They only took 4 steps.
Yeah.
I'm pretty sure they skipped a lot.
You think maybe? Okay. Let's see what we can do.
That was like 20 steps.
Yeah, but that was without having any things you could actually do. Now we'll actually have something. So let's try it. Here we have x, y, dx plus 2x squared plus 3y squared minus 20 dy is equal to 0. Okay? Let's check and see if it's exact. What's our test? Which is xy with respect to y is x is a constant, y is a variable, x. Okay. Whereas the partial of this thing, 2x squared plus 3y squared minus 20 with respect to x is really not that hard.
6y.
It's what?
6y.
That has no x's in it. Partial with respect to x is 0 of this, just like that one. You treat the y's like they're a constant when you're taking the partial with respect to x. Just like here we treated the x as if it's a constant when we took the derivatives with respect to y. So this goes to 0, that goes to 0. What's the partial of 2x squared with respect to x? 4x. They're not equal. But it sure seems like to me that a function, integrating factor mu, that some function of epsilon might make them equal. Possibly. Because there's no y in them. But let's see if what works. Okay? So, we know that didn't work. So let's erase this. Oh, we do need those. So let's not erase them. Okay? No, I hit the wrong button. Okay. All right. Sorry, I lost where I was. Yeah. And the shorthand notation of this was m sub y, and this was n sub x. Okay, just so when we refer to them later, since we will be needing them. Okay, now remember what our two conditions were. That the first case was the n sub x minus m sub y, m sub y minus n sub x divided by n. Okay, so let's see what happens there. Our first condition, the quotient m sub y minus n sub x over n. If that's a function of x and y, we're in trouble. So let's see what we got. We've got x minus 4x over n, which is 2x squared plus 3y squared minus 20. Minus 3x over that mess. You think that's going to be a function of epsilon? No, not a chance. Not a chance. The other condition is this one, that the n sub x minus m sub y over m. Let's see what that is. That's 4x, that's your n sub x, minus x over xy. Okay? And that would be 3x over xy. That would be 3 over y. Is that a function of y alone? Yes, it is. Okay? So therefore, we're going to use that second possibility and say that the mu dy is equal to that thing times mu. Okay? Don't need to write it all down again. We've already evaluated it. It's 3 over y times mu. Right? Okay. So let's do d mu over mu is equal to 3 over y times dy. What does that give us? Okay, this is ln mu is equal to 3 ln y. Right? Well, let's change this and make that ln of y cubed. That's legal in most states, right? Now, e both of them. Right? And that gives us mu is equal to y cubed. There's our integrating factor. So come up here and multiply everything by a y cubed. Okay? So this will be an xy to the fourth dx plus 2x squared y cubed plus 3y to the fifth, right, minus 20y cubed dy is equal to 0. Okay? Now, if you want to be real picky about it, we can check and see if if these are correct. Let's first do our m sub y, this new m that we have here. Take the partial of this with respect to y, and what do you get? Huh? No, no, no. The partial of this with respect to y. 4xy cubed, right? I can't write. Okay, 4xy cubed. And let's do the same here. N sub y, that's an n there. And what is going wrong here? Oh, that's m sub x, n sub x, sorry, n sub x. I was writing m sub y again, n sub x. Take that and you get 4x, this is 4x, yeah, 4xy cubed, and this one, 0, and that one, 0. Yep. Now, the trouble is, now that we got our function that is exact, we still got to do all that, and we're out of time. So, can we pick up next? Aren't we out of time? Okay. Aren't we? Yeah, okay. So, let's pick up there next time. Okay? Let me see if I can figure out where the there is. Okay? We're going to pick up at that equation there. Xy fourth dx plus 2x cubed, x squared y cubed, plus blah, blah, blah. So we'll pick up at that equation and go from there. Okay. All right. Yeah. We almost finished the section, though. Once we get that done, we'll be through. Think you can do any of the odds 1 through 19 that are in the back of the book. Try any of the odds 21 to 25 that are in the back of the book. And you can try 27 if it's in the back. And you can do 29 if it's in the back. And you can hold off doing 31 to 35 unless you just want to give it a shot. Okay? And we'll do the rest of those next time. All right, good deal. Good job. Any questions for we move on? Let me make sure I mark for absent. Okay. So let me end this.